I'm going to be talking about molecular orbital theory. So I've skipped valence bond theory. This is 9A in 11th and 10.1 to 10.2, I think, in the 9th edition. So I'm skipping valence bond theory because I think, and from my experience with working with students, it's much easier to dive into molecular orbital theory. I think quantum transfers easier from the applied system, or from the generalized systems to molecules in MO theory than it does with valence bond. So valence bond theory, again, hybridization, resonance, those sorts of terminology. I think mathematically it's a little bit more complicated to do something with the result. In MO theory, it's easier to get straight through the usage and then get to the result that's meaningful. And the other thing is they both reduce to MO theory. So valence bond theory does reduce to MO theory the deeper you go. We won't go that far, but in quantum or spectroscopy, that MO theory is much more directly applicable. So that's what we will do. I have now MO theory. But if you're going on to grad school in a PChem or synthetic work, once you get through MO theory, jump back into 9A or 10.1 and just kind of breeze through and just kind of read for your fun. Okay, MO theory. What this says, so first of all, number one, Born-Oppenheimer approx, which means that these two nuclei are stable, or not stable, they are stable, not moving, they are stationary with respect to the electron. Okay, so we've got two wave functions that we are going to add together. So the goal is to create wave functions that'll satisfy H psi equals E psi, where these are molecular orbitals. And you do that by adding a linear combination of atomic orbitals. So you're adding together the different atomic orbitals to give you the molecular orbital. So the first off, I'm going to say my psi A, which equals, so I'm going to take a hydrogenic atom. So here, I'll do this color-coded. So we're going to start with this one. So assuming that that's my hydrogenic atom, psi A is equal to 1 over square root pi, 1 over A0, 3/2 e to the minus r, A over A0. So that's the hydrogenic atom. So that's the hydrogenic atom for that system. And so then we have psi B, this one, equals 1 over square root pi, 1 over A0, 3/2 e to the minus r B over A0. Okay, so when you have those two, now what we're going to do is form a linear combination of atomic orbitals. So LCAOs. You may have heard of SALCs, symmetry adapted linear combinations of atomic orbitals. Though we are not symmetry adapting these yet, it's not too complicated, so we don't have to. Linear combination of atomic orbitals. What that means is we are going to have now, and I'm going to designate my MOs with the little serifs, just so you can see that this is the MO atomic orbital. So I've got 1 over square root 2, 1 plus S, psi A plus psi B. Go team. So this is my normalization constant, and S equals what's called the overlap integral. Okay, go team. So what we get is, so there's a great side note example 10.1 in the 9th edition, and I actually don't know the example in there's one example that takes you through what is S. It's in the, there's an example in the 11th edition that takes you through what is S. Oh wait, I can pause and then find it. I was kidding. So in example 9B.1 or 10.1 in 9th edition, it shows you how you get this normalization constant from making sure that psi star psi d tau is equal to 1. Cool, and these are big psis. Okay. Hi. Okay, so I just wrote on the board that we've got psi is equal to the addition, the linear combination of these two orbitals, but we also need to have the difference between them. So we're going to have this. So we're also going to have psi is equal to 1 over square root 2 1 plus s psi a minus psi b. So you can really think of this as big psi is equal to the normalization constant of psi a plus or minus psi b. And I'll explain why we need both a plus and a minus in just a minute. But let's first explore what this would be for psi squared, because remember the probability density is psi squared, not psi. So let's take this one first, and I'm going to label this as plus minus. So psi plus squared equals 1 over square root 2 1 plus s psi a plus psi b. So remember, this is the linear combination of our atomic orbitals. And so I'm going to square this. So that's going to give me 1 over 2 plus 1 plus s. Sorry, that should be times. Times psi a squared plus psi b squared plus 2 psi a psi b. If you recall foiling, so first outside, inside, last. Okay, so that represents now my probability density for my molecular orbital. But if I plot this out, so here's my nucleus A and here's my nucleus B. So what I'm going to have is, so let's draw that one first. So actually, let me get the, oh, whatever. So that's the purple one. So here's my 1s, or sorry, this is my S1 orbital. So the radial distribution for psi A of a hydrogenic atom. And then I've got for psi B, so that's psi B squared. But then what's going to happen is I'm going to have this additional part. So when you add waves together, basically this is what you would get. So the dashed lines so notice how there's still some, if you add this part and this part, so this amount is plus this amount. So if I add this up here, that gives me this total. Okay, so I'm adding the fact that you've got these two waves overlapping each other. And so that's where you get this sort of shape. So this part in the middle here represents the fact that you've got this excess probability density, and that's from this part. And that is where we get what is called, where did I have my notes? The overlap density. Cool. So this is a cross-sectional slice of what it would look like. And really what happens is this is more kind of like this. I just didn't draw them overlapping that much. But you get this overlap density right in between the two A's and B's, or the two nuclei. And so this is what we call a sigma bond, which is positive overlap density. Okay, so you actually have a value here. And this is from Atkins. So bonds form when electrons accumulate in regions where atomic orbitals overlap and interfere constructively. So here you have constructive wave interference. Go team! That's so cool. Okay, so constructive wave interference. Hooray. Now I'm going to stop and I'm going to let you think for a second. What does, so if this one is involving constructive wave interference, any idea why that I had to include the negative the linear combination involving both the positive and the negative. Because not only do waves constructively interfere, they also, go team. Okay, I'm gonna pause and erase this.